So let me give you a mechanical analogy. So we're going to try to come at this in a lot of different ways in the hope of showing. So here's a metastable state. We're going to start with the ball on this side. We're going to roll it over the hill. And there's a couple different outcomes. But the idea is that eventually the ball will end up on one side of the hill or the other. So, in one situation, I give the ball a big push, and it rolls over the top and settles down the bottom. And now it's going to stay there. Is not going to, at least in the sort of physical experiment I've outlined, when I give the ball a single push, once it's over here, the push is over, there's no further changes in the state of the system that I expect. If I don't push hard enough, maybe the ball will roll up the side of the hill and roll back down. So far, so good. And of course, if I'm really, really, really good, okay, how many of you do curling? Okay, so only watching during the Olympics, right? But this idea of getting at just the right amount of momentum that the thing stops just exactly where you wanted it to. I'm not talking about brooms sweeping like mad on the ice. It was the most interesting, shall I say, bizarre sport to watch.
Race walking.
Race walking. Okay, is that even more bizarre? Okay. Anyway, the point I'm trying to make is with just the right amount of push, it is possible that the ball will reach zero velocity, being decelerated by the pull of gravity as it goes up this hill, at just the point that it reaches the top, and there it will sit. Okay, now we all know that that's not particularly stable, a gust of wind, a mechanical vibration. As soon as the ball gets even the tiniest amount of alpha dead center, then the traditional gravitational forces will pull the ball back down to one of the two stable states. So everybody got a sense in which that is not a permanent stable state. It's what we call metastable. It sits there for a while looking stable, but then all of a sudden, zoom, the ball will fall back down. So that's a mechanical analogy. So what does that have to do? Oh, sorry. There he goes. So what does that hill have to do with our electronic system? And if we have a voltage transfer curve, that's shown here in the blue, if we look at the gain of the system, you can see that's what this graph of the partial derivative, partial V out over partial V in. This is the hill that we're talking about, right? And so what we're saying is this is sort of the effect, the acceleration, if you will, that's being provided by the system to a change in input voltage. And basically, as the gain gets steeper and steeper and steeper and steeper, the VTC gets steeper, this diagram of the gain, okay, we get this steeper and steeper hill. But it is possible to end up at a point where you can put the voltage at where the gain of the system is in fact zero. In other words, nothing's going to happen to this output voltage. This voltage is sort of stable until you get to either the voltage just on one side or the other, and now the gain will suddenly, now we have either positive gain or negative gain, and now the system will, the electronics, the amplification provided by the electronics will then produce an output voltage which will go back to one of the bistable states. But there is this magic middle point. Okay, and we can't eliminate it. I mean, the gain goes from being, the change in the gain here goes, we can see it's positive and then sort of peaks and then comes back down. The fact is we do reach a peak at which point the gain seems to be zero. Okay, so it's an inevitable risk that we are going to, when we have these bistable systems, we're sort of stuck with it. So let me see if I can just sort of review what happens, sort of step by step. So what I'm going to do is imagine that my timing of G and D, or between D and the clock, is such that I'm going to balance the feedback loop at exactly this middle point. Okay, and this middle point is the one that the V in equals V out point. So we're exactly balanced. Okay, and what we've done is, because we've been changing D and clock at sort of the same time in violation of the static discipline, we've managed to put this voltage not at a legitimate digital value. Okay, we let the system change, we didn't have D stable long enough for this to always be at a legitimate digital value. By having D violate the static discipline, we've somehow put our system at this metastable point. Okay. The point at which this resolves to 0 or 1 has to do with how far away we are from this balance point, from this magic middle point. We're never, in the world of real numbers, we're never exactly at that balance point. We're going to be maybe very, very close, but we're never, two physical quantities, if you measured them, will never be exactly equal, right? So at least in terms of these voltages. And we are, and I'll show you a little bit more about this in a second, the time it takes to get to a stable value sort of has to do, the amplification of the system is such that the time to settle into a stable state has to do with how far away I am from this balance point. So when I'm very far away, the system has very high gain and will quickly resolve the voltage into a legitimate digital value. When I get closer and closer and closer to it, the time it will take to become stable gets larger and larger and larger. It's theoretically infinite if they're exactly at the middle point, but we're not ever going to be exactly the middle point. But since there's no bound about how close we can come, there's really no bound in how long it's going to take to get to that stable point, right? So if you decide that you're going to rule equality out of physical measurements, that will never be exactly the same, you can at least buy into the argument that the time it's going to take to resolve, as these things get closer and closer together, the time it will take to sort of roll back down the hill gets longer and longer and longer as I get closer and closer and closer to the middle point. Another way to look at that is that if you give me a certain amount of time, I can put the ball close enough to the top of that hill that it won't have resolved to a legitimate digital value in the time that you gave me. Okay. And you can say, I know, I'm going to put noise in the system, so I'm going to, I'm going to have this mechanical, thing, and I'm going to keep shaking the hill. Earthquakes all the time, and that, so now it can't possibly be stable. Okay, I rule that out. So, we're going to build a little thing, an electronic circuit that sits at the side and keeps kicking it in the hopes that will solve this problem. And, you could say, well, gee, that seems like that should work, Chris. And the problem is that it certainly complicates figuring out what's going on. But you can imagine situations where that would have been fine. It wouldn't have reached the metastable state. But because of the noise, you actually put it into the metastable state, so forth and so on. And just as it starts to roll off, you put in some noise which pushes it back. And so noise is not a guarantee of solving the problem. Because you can, if I get to choose exactly, some sort of devil's advocate game I can play, I can take a situation that would have been okay, but noise actually hurts rather than helps.